Hello, today we're going to go on to section 15.4. You might notice in the lecture notes I call it tangent planes and differentials because in this particular section we're skipping the little part that's on linear approximations. I think it's something that's unnecessary and I don't want you to be studying things that you're not going to have on the test or things that we really don't even need. So we're going to go on, and I renamed this section Tangent Planes and Differentials. All right, now what exactly is a tangent plane? What a tangent plane is if you have a surface, here's a surface, all right? If I pick a point on that surface, what the tangent plane is that it's a plane that's tangent to the surface, just touching it at one point around that one point. Just like in two-dimensional space, a tangent line just touches it. In this case, like if I think of my hand here as a surface, and let's say right here where my knuckle is, the tangent plane is going to come down and just touch it at that one point. And the whole idea is for every curve that I can draw in the surface, that curve will be tangent to that plane. All right, now the question is today, how are we going to derive if we're given the equation for a surface, how are we going to come up with the equation for that tangent plane? Now, in the next few slides that I'm going to go through, don't sit there frantically copying. I just want you to sit back and enjoy the show. By the way, these pictures I did in Maple. Okay, I did them on Maple, and what I did is I just selected it and told Maple to copy it, and then when I go back here, I tell it to paste it in my Word document. And you'll find the more proficient you get with Maple, Maple is very, very helpful when you want to do something that's very mathematical. Okay. All right. So what's happening here? First of all, here's my surface, and my surface has the equation z equals f of x y. All right. And I want you to note, first of all, what I did in Maple is I took some surface, and it really doesn't matter what the equation was. I just picked something that would turn out pretty nice in the picture. And what I have here is the plane x equals x naught. So I have some particular point which I'm going to call p naught, x naught, z naught that's on this surface. And I want you to notice that if I take all the points that are on the surface for which x is equal to a constant, that's really the plane, x equals x naught. As you can see, that plane intersects my surface in this curve that's right here, if you can see that curve right there. Okay, and I'm going to call that curve C1. All right, now I'm also going to look at the same surface, z equals f of xy. And again, what I did is I had Maple draw the surface. I had it draw the plane, y equals y naught. And as you can see, the points on the surface for which y is constant is this very nice curve, which I will call C2. All right, so the one curve I got by just picking the points on the surface where x equals some constant x naught, and C2 is the set of points that are on the surface for which y is equal to that constant y naught. All right, and so my next thing is I'm showing both of the curves that are on this surface. The one, x equal to a constant, and the other, y equals to a constant. And notice the two of them intersect in this particular point, which I'm calling point P, which has coordinates x naught, y naught, and z naught. Now what I'm doing right now is I want to show you how we can derive the formula for the equation of the tangent plane to this surface, z equals f of xy, at that particular point, x naught, y naught, z naught. So the first thing I'm going to say is we want to determine the equation of the plane that is tangent to the surface, z equals f of xy, at the point P. We will be looking at the tangent lines to the curves C1 and C2. Now notice, here I have curves 2, here I have curve 1, and what I want to do is I want to get remember back in chapter 14, we learned that if you had a function r of t, right, if you took its derivative r prime of t, and if you evaluated it like at r prime of t naught, you got a vector that was tangent to the curve, right, at the point that corresponded to t equals t naught, right? So I'm looking at, and I want to come up with these two tangent vectors. And remember, this is the particular point right there, which we call P, which is x naught, y naught, z naught. So I would like to be able to find some formula for two tangent vectors. One vector tangent to curve C2, and another vector tangent to curve C1. All right? And notice, if I can get this vector and this vector, you can think of that as sort of like your framework And you can take your plane and lay it on those two vectors, and that will give you your tangent plane. And actually, I had Maple draw the tangent plane. As you can see, my tangent plane's laying right on those two vectors. And if you don't see that it's exact, that the picture's not all that great, what I did is I went into Maple and I had it rotate the picture, and you can see there's the tangent plane, and it's just intersecting that surface at one point. And you can see, if you look real close, I have the two vectors, the two tangent vectors, as lying in that tangent plane. So the question is, how can we find out what those tangent vectors are? How can we derive those tangent vectors for C1 and C2? Again, sit back and enjoy the show. Don't frantically copy every picture, all right? For one thing, I have it posted on Blackboard, so if you want to go back and look at the pictures, you can do it all over again. So, I want to we need to determine the vector's tangent to curve C1 and C2. Now notice, C1, every point on the curve C1 has x equal to x naught. Now the general equation for the surface was z equals f of xy. But for C1, my equation is z equals f of x naught comma y, because every point on the surface has x equal to x naught. So as you can see, for this curve, in reality, you pick just y and you get what z is, because x is already chosen as being fixed at x naught. So as you can see, z is really just a function of y on curve C1. And on curve C2, z would be just a function of x, because y is fixed at y naught. So I have here, on C1, we have x equal to x naught. So we can write z equals to f of x naught y. And what I did was, here's curve C1. Remember, on curve C1, we have x fixed at x naught. So x is not changing. So if I moved my yz plane to go through the point x naught, y naught, z naught, I moved it over. I can think of having a y-axis here, a z-axis here. Here's the point x naught, y naught, z naught. And for that curve C1, you can think of z as really just a function of y. Okay, because why? Because we have this, z equals f of x naught, y. So I'm saying, can I get an equation for this curve C1? All right, and I can very easily, and watch what I'm going to do. If we're on C1, we have z equal to f of x naught, y naught, right? So, just pop that here. Curve C1 can be given as, now, you have an x-coordinate, a y-coordinate, and a z-coordinate. But remember, on C1, x is fixed at x naught, isn't it? And I can choose y, but if I choose my y-coordinate, then my z-coordinate is already picked with the equation z equals f of x naught y. So I can write my curve C1 as x, y, z is equal to x naught, comma, y, comma, f of x naught y. And you can think of this as a parametric form if you want, because your parameter is y. You choose y, and the point on the curve is determined. And we want to get an equation for the tangent vector. Well, how did we do that back in chapter 14? We took the derivative. And if you notice, this function, this curve is really just a function of y. My parameter is y. I'm going to differentiate with respect to y. So I'm going to write this as the partial of r with respect to y is, now I'm going to differentiate each of these components with respect to y. Well, if x naught is a constant, you differentiate any constant with respect to anything, you always get 0. If I differentiate y with respect to y, I get 1. And if I differentiate the function f with x naught fixed and y being able to vary, that's just what we did in our last lecture. It's the partial derivative, isn't it? All right, and this gives me a vector tangent to the plane. Not to the plane, tangent to curve C1. It gives me my tangent vector like I studied in chapter 14. Except if I want the very particular tangent vector that's at the point x naught, y naught, z naught, I will have to plug in for y, y naught. And so my tangent vector, which I'm going to call R1, my tangent vector, which I'm going to call R1, that's tangent to the curve C1, can be represented as 0, 1, and the partial of f with respect to y evaluated at x naught. Oops, we should have had a y naught there. X naught, y naught. I apologize. Little typo there. Those of you that are home, it's going to be fixed when you download it. All right, but my guys in the TV studio are my guinea pigs. All right. So, question.
Why is y equal to 1 then? Like, shouldn't it be y naught over y?
Right here, though, come back up here. We're differentiating y with respect to y, and the partial of y with respect to y is 1.
But over here,
you always have to take your derivative before you put in your values.
Oh, okay.
Okay? Except in this particular case, we're allowed to put x equals x naught in, because when you take the partial with respect to y, x is fixed anyway. Okay? Now, I'm going to do the exact same thing for curve 2. Now, in curve 2, we have y equal to y naught. All right? So, for curve 2, looking at curve 2, same thing. We have y equal to y naught. Our function is z equals f of xy, but since y is fixed at y naught, on curve 2, your z coordinate would be given by f of whatever x is, comma y naught. We want to come up with the tangent vector at x naught, y naught, z naught. Therefore, on C2, we really have z as a function of x. Next, what I'm going to do is I say, OK, on C2, note the following. I could write my curve C2 as my coordinates x, y, z equals. Now we're letting x vary, so x is x, but y is fixed at y naught, and my z coordinate would be f of x, comma y naught. So as you can see, your points are just a function of x. You pick x, and the coordinates of the point on the curve are going to be determined. So to get the tangent vector, why don't we differentiate with respect to x? And the partial of x with respect to x is 1. The partial of y naught with respect to x is 0 because it's a constant. And lastly, we'll just write it as the partial of f with respect to x. Now this is giving me on the whole curve how to get a tangent vector. But I want to get a tangent vector in particular at x naught, y naught, z naught. So I'm going to have to plug in for x, x naught. And we will call that R2. So R2 will be the vector. The second tangent vector, which is the vector that's tangent to curve 2, has components 1, 0, and the partial of f with respect to x evaluated at x naught, y naught. And this is a vector tangent to this curve. Okay, now, in summary, for my two curves, the vector tangent to C1 at x naught, y naught, z naught to curve C1 we've derived was this, and for C2 we got this. These are my two tangent vectors. Don't sit there frantically copying yet. Okay, just want you to enjoy the show for a second. Now you guys tell me, back in chapter 13, you had a vector here, and you had a vector here in the plane, and you wanted to get the equation of the plane. How did we get the equation of a plane? To get the equation of a plane, you needed a normal vector, right? You had to have some normal vector, which was like A, B, C, right? What was a normal vector? A vector perpendicular to every vector in the plane, right? And then you needed a particular point, x naught, y naught, z naught, that was in the plane, right? And what was our equation for the plane? What was our equation for a plane? Once you got the normal vector and you got the particular point, which I'll call him P, what was our equation for the plane? As I recall, it was A times x minus x naught plus B times y minus y naught plus C times z minus z naught. Some of us forgot on our test to put equals 0. Definitely we need equals 0. That was the equation for a plane, right? So if I want to get the equation of the tangent plane, the plane that I can lie on those two vectors, I say, I've got the particular point, x naught, y naught, z naught, but I have to get this normal vector. But I have just got a representation for this vector R2 and this vector R1. So how can I get a vector that's perpendicular to both of those? How can you get a vector perpendicular to two other vectors? Take their cross product. And that's exactly what we're going to do in the next one. And I have this written out for you and posted on Blackboard so you don't have to frantically copy this stuff. Even though I'm not going to ask you to derive this stuff, but I think nobody should use something unless they've seen the derivation. You know, you don't have the right to use it unless you see that why it's true. So we need a plane containing both vectors. A vector normal to both R1 and R2 is its cross product. So now I notice I left out f, the partial of f with respect to y, evaluated at x naught, y naught, because it was too much to write. And the partial of f with respect to x, evaluated at x naught, y naught. I left that out just because it's too much to write. But you guys know how to take the cross product. You're going to take I, eliminate the row and column this is in, and we have 1 times fx minus 0. Then we go minus j times 0 times fx minus fy, and a minus gives me a plus k times 0 minus 1. So this gives me my normal vector. My vector normal to the curve, I'm not going to put a little hat on it because it's not a unit normal, it's just a normal vector, will have components, the partial with respect to x evaluated at x naught, y naught, comma, the partial with respect to y evaluated at x naught, y naught, comma, minus 1. Remember the equation was z equals f of xy. So I have myself a normal vector. Well, if I have the normal vector and I have the particular point, we just reviewed a few minutes ago how you can get the equation for the plane, right? Right? Do you remember why that's true? Do you remember why the equation of the plane is like that? Let's review that for just a second. Notice, if you've got a plane and you've got some vector, which I will call A, B, C, that's perpendicular to the plane, and you have a particular point, which I'm going to put right there, x naught, y naught, z naught. Notice, if you take any point at all on the plane, which I'm going to call as x, y, z, notice this vector from here to here is given by x minus x naught, comma, y minus y naught, comma, z minus z naught. And what do I know about this vector and this vector? They're perpendicular. So what do I know about their dot product? So A times x minus x naught plus B times y minus y naught plus C times z minus z naught is 0. And that's why the equation of the plane is what it is. So going backwards, therefore, a vector normal to the tangent plane at x naught, y naught, z naught is this. And therefore, this is my normal vector. It's not a unit vector, so I'll just put a little bar on it. My particular point was x naught, y naught, z naught. And so we can write our equation as, what's my A? It's f, the partial with respect to x evaluated at x naught, y naught, times x minus x naught. This is like my A times x minus x naught, plus B times y minus y naught, plus C, don't frantically copy this down yet either, z minus z naught equals 0. So we'll have plus the partial with respect to y evaluated at x naught, y naught, times y minus y naught, plus C is just a negative 1, equals 0. Now that one's not as pretty as it is. Notice, since this is minus 1 times this, if I add the z minus z naught to this side, I get my equation looking like that, which I have written out here very, very nicely. Suppose f has continuous partial derivatives. An equation for the tangent plane to the surface z equals f of xy at the point x naught, y naught, z naught is given by z minus z naught is equal to the partial of f with respect to x evaluated at x naught, y naught. Notice this is just a big old fancy A times x minus x naught plus the partial with respect to y evaluated at x naught, y naught times y minus y naught. Okay, coming back here, if you didn't get that, notice I threw this z minus z naught on this side. So we have z minus z naught equals this partial times x minus x naught plus this partial times y minus y naught. That's all it is. So if you have to get the equation for the tangent plane, notice what it is. It's z minus z naught equals, this is the partial of f with respect to x evaluated at your particular point, times x minus x naught, plus the partial of f evaluated at y, evaluated at x naught, y naught, times y minus y naught equals this. And that's the equation for your tangent plane. This you should memorize. I also think this is a good thing to memorize too. If you have the curve z equals f of xy, and you really want to get a vector normal to the surface at x naught, y naught, z naught, this thing that we derived I think would be very helpful too. So with all that we've gone through, an equation for a normal vector and the equation for the tangent plane probably are two things you want to put aside. Put on your little cheat sheet. But also, it'd be nice to have it in your head. All right, so let's practice a little bit. Determine the equation of the tangent plane to the elliptic paraboloid z equals 2x squared plus y squared at the point 1, 1, 3. This is our particular point. Okay, our equation is z minus z naught equals the partial of f with respect to x evaluated at the particular point times x minus x naught plus the partial f with respect to y times y minus y naught. That's our equation that we're going to plug in. We already know x naught, y naught, and z naught. So I can put that part in. My x naught, my z naught's 3. X naught's 1. Y naught's 1. So I have these two things yet to fill in. This little piece here and this little piece here. Piece of cake. Z is equal to f of xy. So what is the partial of f with respect to x? Well, if z equals 2x squared plus y squared, partial of f with respect to x is 4x. So the partial of f with respect to x evaluated at 1, 1, 3, just put a 1 in for x and you get 4. And what's our partial of f with respect to y? Well, here's our function. It's just 2y, isn't it? So the partial of f with respect to y evaluated at 1, 1, 3. The only one to plug in is y is 1. I get 2. So the one coefficient's 4 and the other's 2. And I think this is a beautiful way to have your equation, but I guarantee your book's not going to have that. They're going to multiply things out. Z minus 3 equals 4x minus 4 plus 2y minus 2. So z equals 4x plus 2y. And this is a negative 4 and a negative 2 is a negative 6. And if you add 3 to both sides, they'll probably write it as z equals 4x plus 2y minus 3 as their tangent equation. But all you had to do was this. Remember this. The thing to remember, though, for these partials, I get students all the time on their test. They'll do the partials and they'll put 4x in front of here and 2y in front of here. No, 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 no. You have to evaluate your partials at your particular point. Otherwise, it's not going to be the equation of a plane. Not hard. Let's do another one. Okay. How about this one? Find an equation of the tangent plane to the surface z equals e to the x squared minus y squared at the point 1, negative 1, 1. So z equals f of xy, which is e to the x squared minus y squared. Okay, now the reason I chose this is I found that a lot of students need to review their exponentials. And you know, we already know the equation for the tangent plane is this. So I say, you know what, I got to get my two partials. Let's do that first. So let's see, what's the partial of f with respect to x? Well, let's see, the derivative of e to the u is e to the u, right, times the derivative of u. And since we're taking the partial with respect to x, the derivative of x squared minus y squared with respect to x is 2x, because we consider y to be constant. So if we want to evaluate this at the point 1, negative 1, 1, notice the z part you could leave out if you want, but it really doesn't matter. You're plugging x in for this, y in for that, and z in for that. I get, let's see, e to the 1 squared minus 1 squared is 0, times 2 times 1 is 2. E to the 0, last time I looked, it was 1. So I have 1 times 2, which is 2. Okay? Now let's get the partial of f with respect to y. And that's going to be e to the u is e to the u times the derivative of u. And derivative of x squared is 0 minus derivative of y squared is 2y. So right here I have, if I want to evaluate the partial of f with respect to y at the point 1, negative 1, 1, I get e to the 0 times 0 minus 2 times y is a negative 1 e to the 0 is 1. So it's 1 times 2, which is 2 again. All right, and we know now our equation for the tangent plane, which we're going to have memorized, is z minus z naught equals partial of f with respect to x times x minus x naught plus partial of f with respect to y times y minus y naught. And let's see, our particular point is 1, negative 1, 1. So it's going to be z minus 1 equals, my first partial was 2, my x naught is 1, my second partial was 2, and my y naught is minus 1, so minus a minus 1 is plus 1. And let's see, that gives me z minus 1 equals 2x minus 2 plus 2y plus 2. It looks like the 2's cancel. So it would be z equals 2x plus 2y plus 1. Now we did 2 of those. I think that's plenty. Okay, but you guys are going to do about 3 or 4, okay, because you've got to practice. Okay, and where do we mess up? Do you know where we mess up? We mess up differentiating a cosine. We messing up differentiating a logarithm, right? And that's part of it, is bringing that stuff back and practicing. All right. Now, you're going to notice I'm skipping all the epsilon delta stuff in this section. We don't really need it to get good answers. And so my definition for differentiable is a lot different than the book's. I'm taking the theorem that the book proves as my definition. But we're going to use a function f of xy is said to be differentiable at the point AB if the partial derivatives exist near AB and are continuous. So notice this is f of xy here is a function of 2 variables. Your AB is some point here. We're saying if you can, when I say near AB, just put a little disk around AB. If your partials exist in that little disk and are continuous, we say the function's differentiable at that point. And we're not going to do a whole lot of theory, but that's what we'll use later on when we read a theorem and they say that f is differentiable at some point. We'll say, oh yeah, the partials exist and they're continuous. All right, now, notice before we even start all this stuff, let's go back to Calculus 1 for just a second. Do you remember when you had a curve and you picked a particular point on the curve, all right, and you found the equation for the tangent line? Do you recall that if you took a small neighborhood around that point and just looked at that, the tangent line was a fabulously good approximation for the curve, right? They were very, very close to each other. When you got further away, the approximation wasn't so good. Okay? All right. What we're going to look at is now having a surface in 3-dimensional space. And I have some point here, and I have a tangent plane, tangent to the curve at that particular point. And we're going to look at the plane, especially when you're in a small neighborhood around that particular point. The plane is an excellent approximation to the actual surface of the actual surface. Okay? All right, so recall that if z equals f of xy, the equation of the tangent plane to z at the point x naught, y naught, and I'm going to call it f of x naught, y naught, which we could also call z naught, is given by, and we just did 2 examples like this, so we should be okay with that. All right? So now, delta z, if you go from z naught to the point x, y, z, you with me? If I'm going from a point on the surface, x naught, y naught, z naught, to some other point x, y, z, we could say z minus z naught is how much z changes. Delta z is equal to z minus z naught. So we could write delta z is equal to the partial of x, blah, 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 using the same formula. All right, now notice, this delta z, this is the equation on the plane. All right, this is the equation on the plane. So if I move on the plane from some point x naught, y naught, z naught to some other point x, y, z, we could compute exactly how much z changes on the plane using this equation right here. All right, but let's look. if the surface looks like this is a sideways view of the surface, all right? I'm going to make it be some cylinder that I'm dragging out. And let's have the tangent plane right here looks like this. And let's let this be the y-axis and this is the z-axis, just so I'm getting a cross-section so I can see it a little bit better. If this is my point x naught, y naught, z naught, and this is my point x, y, z, notice, if I draw a parallel right here, this is how much z really changes on the surface, on the curve. All right? This, I need a different color. I guess black will have to do. Now let's use my pencil. This is how much z changes on from this point to a corresponding point on the plane. You with me? If I look at points that have the same x naught, y naught coordinates. Okay? Now you can see, go, gee, Mrs. Strocko, how much z changed on the surface is a whole lot different than how much z changed on the plane. Except, what if I make it be a very small interval around that point? Then all of a sudden, how much z changed and how much it changed on the surface and how much it changed on the plane are they're very close, right? The one's a very good approximation of the other. We all okay? All right. So this delta z is how much z changes on the tangent plane. But I'm saying to myself, well, gee, now notice the x minus x naught, you could call that delta x, how much x changed, and the y minus y naught, you can call that delta y. So if I want to come up with an approximation of how much z changes on the surface, as long as delta x and delta y are relatively small, this would be a very good equation, right? To give us a good approximation of how much z changed. Welcome to the world of differentials. How much z changes on the tangent plane is very close to how much z changes on the surface when we are close to x naught, y naught, and f of x naught, y naught, which is your z naught. Therefore, when delta x and delta y are small, a very good approximation for delta z is this. And where did I get it from? I just got it from the equation of the tangent plane, saying, z minus z naught would be delta z, x minus x naught is delta x, y minus y naught is delta y. All right? Notice, since these are not equal, I'm going to call what's on the right-hand side I'm going to call it not delta z, I'm going to call it dz. All right? And I'm going to give it a name. I'm going to call this the total differential. And what we just proved, this is a very good approximation for how much z changes when delta x and delta y are small. So, definition. In terms of what do I need to copy down, you want to copy this down. All right? If z is equal to f of xy, then the total differential, which we will call dz, is defined to be the partial of z with respect to x dx plus the partial of z with respect to y dy. Now you might be sitting there thinking, well, what the heck is dx and dy? For your independent variables, what are my independent variables? They are the guys that you plug into the formula to get the third guy. You plug them in and then z depends on them. For the independent variables, delta x and delta y are one and the same as dx and dy. All right? So this is what our definition of the differential is. dz is the partial of z with respect to x dx plus the partial of z with respect to y dy. Why do we care? Because dz, when delta x and delta y are relatively small, is a very good approximation for delta z, for the actual amount that the function changed in terms of the z coordinate. Okay, so first of all, we got to practice. And it's imperative that everybody in here, when I ask you to determine the differential of this function, you can do it. Piece of cake. Notice this function z is a function of two variables, x and y. Z is equal to x squared plus y squared. So according to our formula, dz, which is called the total differential, is the partial of z with respect to x times dx plus the partial of z with respect to y times dy. And it's a wonderful measure of how much z changes. Now all we have to do, guys, is fill in. What's the partial of z with respect to x? 2x times dx plus, what's the partial of z with respect to y? 2y times dy. Done. We have computed the total differential. In a few minutes we'll see what we can do with it, but there's more than we can do with it than just is in this section. We're going to use a lot of stuff for it. Okay, can I do another one? This one. Ugh. Notice here, v is a function of x and y, right? Because I got y times cosine of xy. So dv is going to be the partial of v with respect to x times dx plus the partial of v with respect to y times dy. Except now let's see here. dv is equal to, we got to take the derivative of that, the partial of that with respect to x. So if we're taking the derivative with respect to x, we consider y to be a constant. So a constant times a function, you just take the constant. Derivative of cosine is minus sine of what's inside times the derivative of what's inside, and we're differentiating with respect to x. So what's the derivative of x times y if we're differentiating with respect to x? Y, yeah, right, because it's like a constant. So it's going to be times y, so I'll have a y squared out there. Don't forget the stinking dx. You go, why is that stinking dx there for? Because if we went back, let's see if I can pull it back, where this whole thing was derived from the equation of the tangent plane. Notice what we have here is delta z equals partial of f with respect to x times delta x plus partial of f with respect to y times delta y. There's your partial, that's how much x changed. Here's your partial, that's how much y changed. So that dx and dy are representing how much x and y changes. If you leave that dx out, you won't get any credit on the test. So you just have to practice. Plus, now you guys help me here. I'm differentiating this with respect to y. So when I differentiate this with respect to y, I think I have two parts. It's like a u times a v. So we got to take the first, which is y, times the derivative of the second. The derivative of cosine is minus sine of what's inside times the derivative of xy with respect to y is x. Plus the second, which is cosine of xy, times the derivative of y with respect to y is 1. Don't forget your dy. Okay. So it's the partial with respect to x times dx plus partial with respect to y times dy. It's imperative that you don't forget that dx and that dy piece. All right, let's do one more. This one's not all that hard, but it's imperative to notice. Here, w is a function of x, y, and z. I didn't give you a definition for the differential of a function of 3 variables, but I think you can use your imagination, right? What do you think it's going to be? dw is going to be the partial of w with respect to x times dx plus the partial of w with respect to y times dy plus the partial of w with respect to z times dz. So dw is, partial of that with respect to x, I picked something really easy. It's 3x squared. Don't forget your dx. It's wrong if you don't have it. Plus, the partial of this with respect to y is 2y. Don't forget your dy. Plus, the partial of that with respect to z is 5z to the 4th. Don't forget your dz. There's your total differential. Okay? Now we're going to be using this total differential for a lot of neat things. But one thing we can use it for is to remember delta z and dz are two different things. Delta z is how much the function really did change. The differential is an approximation to how much it changed. Okay, now in this problem right here, they say z is equal to x squared minus xy plus 3y squared, and xy changes from 3, -1 to 2.96, comma, -0.095. All right, so delta z Just like if you asked me, oh, Mrs. Strocko, you were on a diet, how much weight did you lose? I'd take my final weight minus my initial weight, right? Right? And that would tell you, like if I weighed, if I weighed 120 pounds, let's say 150 pounds now, and in a month, let's say in 3 months, I'm down to 140. How much did you lose? Don't you go 150 minus 40, you're going to go 140 minus 150. Your change in weight, Mrs. Strocko, was 10 pounds. Negative 10 pounds. We always take final minus initial to get our change, right? Okay, so if we want to get delta Z, we want to take Z final minus Z initial. So in this case, the final was Z evaluated at 2.96 comma negative 0.95 minus Z evaluated at 3 negative 1. And your function Z here is x squared minus xy plus 3y squared. That's a little bit tedious to plug those in. Okay, so I'm going to show you how we can do it on our calculator. Does everybody have that copied down? It's Z of 2.96 comma, it's always your final because you're going from here to here, so that's your final minus your initial. 2.96 comma negative 0.095 minus Z of 3 comma negative 1. Now you realize to figure out this Z of 2.96 comma negative 0.095, you're plugging 2.96 in for x and a negative 0.095 in for y, right? We all understand that. But the TI-92 is pretty cool. Let me show you what I can do on the TI-92. Pulling down here so we can see the function that we want to evaluate. That's my function. I'm going to turn it on. All right. There's this real cool button on the TI-92 called F4, which is define. All right. I hit F4, and option number 1 is define. So I hit define there. Okay. Now watch what I'm going to do here. You guys are seeing. Wonder why. It's sort of like transparent, huh? Let's make this be like that so you can see it better. And the function I'll just put right here so you can see it. That will be better. All right, so I'm going to hit define. I'm going to type F parentheses x comma y close parentheses equals. My function is x squared. Oh, I didn't do a y there, did I? Let's go back here. It's x comma y. And it's x squared minus x. Just like in Maple, you have to go times y, plus 3 times y squared. And I hit enter. And in my function right now, f of xy, f has been defined to be f of xy as x squared minus xy plus 3y squared. Now we wanted to figure out, right here, what was f evaluated at 2.96 and a negative 0.095. So I can go f parentheses 2.96 comma, a negative 0.95. And I get 14.2811. If I wanted to get f evaluated at a negative 3, comma, negative 1, close parentheses, f evaluated there is 15. Now notice with the calculator, if I go up here, there's the first number. I can hit enter and pull it down, minus, go up and highlight the 15, pull it down. We wanted to take that minus that, hit enter. It's a negative 0.7189. Delta Z is how much the function really did change. Just evaluate the function at final minus evaluate the function at the initial. That's what they wanted me to figure out, delta Z. Delta Z is how much did it really change. Now they want me to evaluate dz. Okay, so let's get rid of the calculator for a minute. Let's turn it off. Then maybe in the TV studio they'll realize I turned it off. And the function was z equals x squared minus xy plus 3y squared. And they want me to figure out the total differential dz. No problem. Notice, first of all, ask yourself, z is a function of how many variables here? 2, x and y. So the dz is the partial of z with respect to x, dx, plus the partial of z with respect to y, dy. So dz is going to equal, let's see, what's the partial of z with respect to x? Partial of x squared is 2x. Partial of xy with respect to x is y. Partial of y squared is 0. Plus the partial of x squared with respect to y is 0. Partial of xy with respect to y is x. Partial of 3y squared is 6y. Okay, everybody with me? Now, we plug in initial values for x and y. All right? So our initial values were x was 3 and y was a -1. We're going to do that in a second, but also for dx, we plug in delta x. Now what's delta x? How much did x change? Well, how much did x change? It's always x final minus x initial. So it's 2.96 minus 3, which is, what is it? Delta x, or dx, is going to be a -0.04. And dy is delta y. That's y final, which is a -0.95, minus my initial, which is a -1, and that's going to be what? A +0.05. All right. What are we plugging in for x and for y? The initial values, which were 3 for x, and for y, I'm plugging in a -1. Everybody with me? So for x, we're plugging in 3. For y, we're plugging in -1. For dy, we're plugging in 0.05. And for delta x, we're plugging in a -0.04. So coming up here, dz equals 2 times 3 minus, now what's going in for y? A -1, so it's minus a minus, which is plus. Delta x was -0.04 plus minus x is a -3 plus y was a -1, so 6 times a -1 is a -6. And what goes in for delta y? Positive 0.05, was it? So I have 6 times 3 is 2 times 3 is 6, plus 1 is 7. So I have 7 times a -0.04 plus a -9 times 0.05. Now I think I'll turn on my calculator just to do this calculation. And let's see, I'm going to have 7 times a -0.04 plus a -9 times 0.05. And I'm getting, can anybody see it? 7.3? Negative. dz is a -0.73. What was delta z? Delta z was, dz was a -0.179 and dz was a -0.73. As you can see, dz, when delta x and delta y are relatively small, is a very good approximation to this. Okay? Now let me show you some examples of what we can use this for. Okay, first one I want to use is the following. The base radius and height of a right circular cone are measured as 10 centimeters and 20 centimeters respectively, with a possible error in measurement of as much as 0.1 centimeters in each. Use differentials to estimate the maximum error in the calculated volume of the cone. How many of you are taking physics and chemistry right now? And your instructors in your labs tell you to do an error analysis. And they have these bizarre error analysis formulas. And you're wondering, where did they ever come up with these? They came up with them from the total differential. That's where they come from. Go back and look in your chemistry lab and you see a product and you look at how they do their error analysis, it comes from the product of x times y. All right, so now what we're going to do first of all is, we're talking about the volume of a cone, right? Yes, the volume of the cone. Does anybody know the formula for the volume of a cone? I hope and pray that in Calc 3 you know it, but also in the front flap, back flap of your book we have those. And the formula for the volume of a cone is 1/3 pi r squared h. That's the formula for the volume of a cone. Notice this formula is a formula of two variables, the radius and the height. It's a multivariable function. Now, what are they giving me so far? They're saying the base radius and the height have been measured to be 10 centimeters and 25 centimeters. Let's all remember our unit is centimeters. I don't feel like writing the centimeters out continually. All right, in physics and chemistry they do all the time, but I know everything's in centimeters, I'm okay. So my radius is 10 and my height is 25. But I have a possible error of 0.1 centimeters. So that's my delta R and my delta H, because my R could vary by plus or minus 0.1 centimeters, and my delta H could vary by plus or minus 0.1 centimeters. Okay? Now we want to come up with a way of estimating how much could our volume be off by. But instead of evaluating delta V, we're going to evaluate dV. V is a function of R and H, so dV would equal the partial of V with respect to R times dr plus the partial of V with respect to H times dH. It's that simple. So dV is equal to, now you guys tell me, if V is 1/3 pi r squared H, what's the partial of V with respect to R? Bring down the 2, you'll have 2/3 pi r, and H is a constant, so just bring him along for the ride. Are we all okay? What's the partial of V with respect to H? 1/3 pi r squared is your constant, so it's a constant times H. A constant times H, its derivative with respect to H is just 1/3 pi r squared times dH. Now remember, what are my independent variables? R and H. So delta R and delta H are one and the same as dr and dH. So to estimate dV, what are we plugging in? We're going to plug in 10 in for R, 0.1 in for delta R, H gets 25, and delta H gets plus or minus 0.1. To get maximum error, I'm going to make both of those be positive. All right? So playing plug in, let's see what we get here. We're going to go 2/3 pi, R is 10, H is 25, delta R is 0.1, plus 1/3 pi, R is 10, 10 squared is 100, times dH, which is also 0.1. So let's see, before I do anything, let's see. 25 times, let's see, 10 times 25 is 250. 250 times 2 is 500, times a tenth gives me 50. 100 times 0.1 is 10. So it looks like I have 60 pi over 3, which is 20 pi. All right, and what's 20 times pi, if you want a decimal? What is it? 62.8. And that will be centimeters cubed because it's volume. So just by having your radius, think about this, this is pretty incredible. Just having your radius off by 0.1 and your height by 0.1, your maximum error is 62.8 cubic meters. Okay? Neat. So you don't have to memorize those formulas anymore in chemistry and physics. You can derive them yourself. Let's do this one. The dimensions of a closed rectangular box are measured as 80 centimeters, 60 centimeters, and 50 centimeters respectively, with a possible error of 0.2 centimeters in each dimension. Use differentials to estimate the maximum error in calculating the surface area of the box. Well, first of all, we're talking like a shoebox. Here's my shoebox. And what are we calculating? The surface area. Well, what are the dimensions of the box? We could use length, height, width. I'm going to use x, y, z's because they're easier to write. X, y, z. All right, now we got to come up with a formula for the surface area of that box. Well, if you notice, look at my surface, at my box. Do you see you have a bottom whose area is x times y? And you have a top whose area is x times y. So I have two sides that are x times y. Then you have this side here whose area is y times z. but you got its sister one over there, which is y times z. So we have two rectangles whose area are y times z. But then we got the front piece right here, whose dimensions are x by z, but you got one in the back that goes right with it. So that is the area, the surface area of my box. Notice my surface area is a function of x, y, and z. Shall we compute the total differential of s? ds is the partial of s with respect to x times dx plus the partial of s with respect to y times dy plus the partial of s with respect to z times dz. All right, so let's see if we can compute this. ds is equal to, let's see, if we're taking the partial with respect to x, you'll have 2y plus, that's a 0, 2z times dx plus the partial of s with respect to y is going to be 2x plus 2z times dy plus partial with respect to z, that one's 0, that'll be 2y, and that one will be 2x times dz. Okay. Now I have to figure out what numbers to plug in, so let's go back and look. What numbers can we plug in? Let's look right back here. They say that the dimensions are 80, 60, and 50, so I'm going to let x be 80, I'm going to let y be 60, I'm going to let z be 50, and with a possible error of, so delta x, delta y, and delta z are all going to be 0.2. Okay, so plain plug in here. We're going to get, well, let's fold this down so you guys, I hate it when you can't see everything that I'm doing. Limitations of a TV screen. All right, plugging that in right here, you're going to have 2 times y, which is 120, plus 2 times z, which is 100. For delta x, we're putting in 0.2, plus 2 times x, which is 160, plus 2 times z, which is 100, times delta y, which is 0.2, plus 2 times y, which is 120, plus 2 times x, which is 160, times 0.2, and 0.2. And I already punched this into the calculator, so instead of turning it on, take my word for it, we're going to get 152. And what's the unit? It's surface area. So what's the unit going to be? Square centimeters, right? Isn't that neat? You can use total differentials to do an error analysis, and that's exactly where they came in chemistry and physics. One more. Whoops. I better have one more. Yes, one more. Okay. Use differentials to estimate the amount of metal in a closed cylindrical can that is 10 centimeters high, 4 centimeters in diameter, if the metal in the top and bottom is 0.1 centimeters thick, and the metal in the sides is 0.05 centimeters thick. Now, a can, last time I looked, is not solid. Do we all agree about that? Okay, it's hollow, all right? A can, you know, you got the Campbell soup in the inside, but the tin is just the periphery. But if we draw the can, you know what I'm talking about? The part that's the material you could think of is how much does my volume change if I increase the diameter from 4 centimeters to, what's the air? Let's see, what do we have here? They say that it's a closed cylindrical can that is 10 centimeters high. So its height to begin with is 10 centimeters. Its diameter, which I'll call d, is 4 centimeters. So its radius is 2 centimeters. All right? And the metal in the top and the bottom is 0.1 centimeters thick. So if you started out with these amounts, okay, but then you increase it, you with me, or decrease it, if the top and the bottom are 0.1 centimeters thick, how much is your height changing when you take into consideration the points? Beautiful. Your delta H is 0.2. Perfect. Because you see you got 0.1 on the top and you got 0.1 on the bottom. Now, the metal in the sides is 0.05 centimeters thick. So what's my delta R? It's going to be 0.05, right. Do we all see why we had to double it with this? Because the top and the bottom, you've got a top and a bottom when you're measuring your height that change. But the height, the radius, you're just going from here to here, so your delta R is just 0.05. And the amount of metal that we want to come up with is delta V. How much does our volume change when we increase our sides by so much and our height by so much? So what we want to come up with is dV. What's the formula for the volume of a Campbell soup can? Pi r, whoops. Let me get another piece of paper because it's not pi squared, it's pi r squared. Volume is pi r squared h. Notice your volume is a function of r and h. So my total differential dV is partial of v with respect to r dr plus partial of v with respect to h dh. And dV is, let's see, what's the partial with respect to r? 2 pi rh times dr. And what's the partial with respect to h? Pi r squared, right? Times dh. And now we have a bunch of things to plug in. So let's see. For r, we're plugging in 2. For h, we're plugging in 10. For delta r, we're plugging in 0.05. For r, we're plugging in 2. And for delta h, we're plugging in 0.2. And again, I already popped this into the calculator. It turns out to be 8.8, and it's going to be cubic centimeters because it's a volume. Okay, so we're estimating this dV, which is actually what the can needs to be, is about 8.8 cubic centimeters. Okay, we need to practice. All right. Notice I want you to read pages 959 to 965. There's a little part that it's actually labeled linear approximations. You can skip that. I mean, if you really want to read it, fine. The bottom line is a tangent plane is a linear approximation to the surface. They're just rewriting the equation of the tangent plane. That's all they're doing. So I'm figuring why. We already know that the tangent plane is a good approximation, so leave it at that. Then I want you to do on pages 966 to 967, just 1, 3, 5, and then 23 to 33, the odds. All right, I'll see you next time. Bye-bye.